Hi, I'm Wes Mason, and my group partners are Caleb Fisher and Anthony Mangio, and we're going to talk about our semester project, specifically today for Electronics 321. We had the semester project, and part of the requirements was to have at least a diode, a transistor, and an op amp. So we decided to do a project that involved taking an audio signal, so the voltage from a headphone jack, and equating the amplitude at certain frequencies to a light intensity. So to do that, we came up with these steps for our project. So we have our input, and then we're going to run it through our frequency filter. And then once we've filtered it to the frequency we want, we just want to figure out what the amplitude of that wave is. So we're going to take a sine wave essentially, and then we're going to convert it to an analog voltage. And then this part is actually for 376, but we're going to do an analog read, figure out what the voltage is there. And then we're going to communicate to another PIC and do a PWM conversion based on the analog read. So we're going to relate the voltage we read to a duty cycle. And then this portion here at the end is actually driving the LED array for a light intensity, and that's going to be controlled by the duty cycle of the PWM. So to start, right now I just have a signal generator playing on this, and it's outputting a plus minus 1 volt sine wave. And you can see that the PWM output to the light intensity here is at about 40%, so it's operating at 40% brightness. So to follow this through, we start here with the audio coming in, and I just took a headphone jack and cut it here, so we connected all the grounds together between the two PICs, and this is the frequency filter, this is the envelope detector, and this is the LED array. So the signal's coming in here, going through the frequency filter. This filter is a third order Butterworth, and it was designed to reject frequencies over 200 Hertz and pass the ones under. And we also put a gain of 2 in at DC, so we get a little bit of amplitude out of it. So we have a 1 volt wave coming in. If we were to check the output of this, it'd be about a 2 volt half wave rectified. And that goes into our envelope detector. And what this does is charges the capacitor through this diode, and then when the op amp goes low on the lower portions of the wave, the diode cuts it off so it can't go to ground, and it just discharges through this resistor. So you get a charging, and then you get a little bit of ripple out. So it takes our half wave rectified signal and equates that to a DC analog voltage. This is the output from that, and it's connected to pin A1 of our A to D read PIC here. And this takes a reading of the voltage on that pin, and it equates it to a number. 0 volts in would be the number 0, and 5 volts in would be the number 1023. So we have 1023 degrees of resolution. For this project, we have a 1 volt wave in, maybe 1.5 when we play music and there's a spike. So we predicted the maximum voltage in to be about 3 volts. So the highest reading we should get on this is about 600. This PIC takes that number and converts it to a 3-digit ASCII message and sends it serially to this PIC processor. So it transmits on RC6, and this PIC is going to receive that message on RC7. So you can see that it's displaying the same numbers that were on the other screen. This second number down here is the calibration function that we implemented to do the PWM. Our PWM period is 10 milliseconds, and the interrupt routine that services it is 50 microseconds. So you have 200 degrees of resolution, 10 milliseconds divided by 50 microseconds, and that's how fast we can get in there and be able to toggle that pin to control the duty cycle. So this number relates directly to the voltage read here, and like I said, 600 is our max predicted, so the calibration function sets it anything over 600 is just 100% duty cycle, or 200 services, so on all the time. Right now it looks like we're at about 95, which would be a duty cycle of 47%. So this is our LED being powered by the PWM. It consumes 1 watt of power. So the signal comes in here on the base of the transistor and then lets current flow through. So it's either off or in the saturated region. We designed that in. So to give you a demonstration with a song here, we can turn off the frequency generator. And we'll start to play a song. So now you see it's still a AC signal between plus minus 1 volt. The PWM is changing with the music here. So if there's more noise at low frequencies, like when a bass note hits, the PWM gets larger, otherwise it shrinks up. and you can watch the LEDs over here pulse with the music. Okay, thank you. We're going to talk about the frequency filter for our semester project. So to design it, our requirements for this is the input was tested off of a cell phone jack to be plus minus 1 volt AC. We're concerned with the signal at low frequencies for this project, so we made our requirements for the output to be a half-wave rectified AC signal. So we're going to lose the bottom part, but that's all right because of our next section. And then we want to have a gain of 2 at DC. We also want to have our corner frequency be 200 hertz, so we'll have a gain higher than 0.9 at 200. And over 1,000 hertz, we want to have a gain of less than 0.1. So we picked a third order Butterworth filter to be the kind of circuit we wanted to implement. If you come here, the transfer function that we implemented is this, right here. So to design that, we went into MATLAB and we picked a couple things. We knew that our R1 and R2 are voltage divider. We wanted those to be 10,000 ohm, and we just picked a capacitor that was available. And using that information and the transfer function, we were able to solve for the resistors for our filter over here. And we simulated that just by doing 1 to 2,000 hertz. And these are the results we got back from MATLAB. So at DC, we have a gain of 2. This dot here is our corner frequency, and you can see that the gain at 200 hertz is roughly 1.9 still, so it passes over that. And then down here is our other corner frequency at 1,000, and you can see the gain there is about 0.3, so it passes. And this graph here is just the same information but in decibels. So once we had verified that our calculations were good with MATLAB, we went to LT Spice and we actually built that circuit. So this is the same circuit you saw there, but with the values inserted for the resistors and the capacitors. And then this is the op amp. So this section here is the first order filter, and then this is the second order portion here with the feedback that allows us to get a gain of higher than 1. We simulated it on LT Spice, and we got a little lower values here. It says we're only going to get about 6 decibels at 0 hertz, but we still have a little bit of resonance, and at 1,000 hertz we are down near minus 20 decibels, so definitely below the 0.1. This is a demonstration of the third order Butterworth filter that we designed. So over here we have the filter. This is our input and this is our output, and then this is the first order filter section here. This is the second order. Over here is the envelope detector. They're sharing the same op amp, so it passes this signal right over to the other side for the next section. So for this portion though, right now we're inputting a 1 volt AC wave. It's at about 10 hertz, and you can see that the gain we're getting out is about 2. So if we increase the frequency here, you can see it start to go down. Right here is our gain of 1 point, and for this filter that we implemented, it's not what we had expected. This is at about 100 hertz, so as we keep going up, it starts to go down more. So the filter that we designed is outside of the tolerance for our project. We'd actually built a second one. The first one we built was on a breadboard, and that one had tested better, but the one that we implemented on the solder board had a quarter frequency at a different point. We decided to keep it for the project though, because it still passes the low range frequencies, just not as much as we'd hoped for.
This is the envelope detector portion of our semester-long project for ECE 321, and we'll start with our requirements. We wanted a input of 1 to 200 hertz, 0 to 3 volt half-wave rectifying AC signal. We wanted that to output a 0 to 3 volt DC voltage, and we wanted a ripple of less than 10%, and we wanted that output to be as much of a DC signal as possible. And then we also we just took our basic envelope detector circuit, and the main things we wanted to find here was our resistor value and capacitor value. And then down here we use this equation to find our capacitor value. We know the current because it's the max amount of current that the op amp can output, and then we have our difference in voltage over our difference in time. And our time, we used 50 hertz because we thought that was a reasonable amount between our low point and high point, so that was our design point. and we plugged this into MATLAB, and it gave us 80 microfarads was our max. So we used 8 just to be on the safe side, 8 microfarads. And then, knowing our capacitor, we can come down and find our resistor using this equation. And this told us that our minimum resistor value could be 1,000. We used a 10K resistor just to be safe. And then, knowing those two things, we found our ripple using the equation, this equation here. And that told us our resistor value would be our ripple would be 0.1. Knowing all this, we plugged our numbers into LT Spice, and it gave us what it would look like. Here's our input, half-wave rectifying AC signal, and then this is our envelope detector catching the peaks for our output. This is saying that our ripple is about 0.2, but that is okay because it is still within our requirement. This is a demonstration of our envelope detector working. Over here we have our circuit for our envelope detector. This half is our filter earlier. They're just sharing an op amp that's in the middle. And then over here we have an oscilloscope hooked up. This is our input, our half-wave rectifier, and this is our output for our envelope detector. And I'm just going to shut off our input so you can see a little better. And there is our input. The ripple is about 0.1 there, as shown in MATLAB predicted. And if I change the voltage, if I lower it, it gets even better. And if I turn it up, it's still about 0.1 volts. It doesn't change too much. I'm going to turn the frequency down. That was for our design point of 50 hertz. So I'm going to turn the frequency down, and it's about 10 hertz here. And if I scale it, if I put it down, you can see the ripple a little better. The ripple is just a little bigger. This is outside of our design, so it's not a big deal. But this just shows that the envelope.
Alright, so this is the final part of our electronics 321 project. So we had an input of 5 or 0 volts square wave, and an output we wanted an LED array that could dissipate 1 watt of power. So this is the calculations portion of the transistor switch part of our project. We had 5 volts coming in from the power supply. We wanted 1 watt of power dissipation, so we knew the current going through the LED array needed to be 200 milliamps. We broke down this requirement into 10 separate LEDs running at 20 milliamps, and it took 3 volts to turn them on. Each of these had a resistor in series with them, 100 ohms. This was enough to power the 1 watt energy dissipation. In order to make sure that the transistor was in the saturated region, we picked a value of R base, which we which was 1,000. This led to enough current flowing through the base to saturate the entire transistor. So this is the simulations portion of the transistor switch section of our term project. I want us to look at the voltage across the diode, and we can see over here when the diode is on, 3 volts are going across it. This means that 2 volts are going across the resistor, giving us 20 milliamps, thus giving us 1 watt of power dissipated throughout the LED array, which verifies our design.